Good morning. I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today I am going to discuss the bias circuit of IC741. As we all know that this is the pin diagram of IC741 and we all are familiar with this. That means this is the 8-pin IC. And we all know the function of various pins, like this is offset null, this is inverting input, pin number 2 is non-inverting input, and pin number 3 is non-inverting, 4 is negative power supply, 5 is offset null, 6 is output, 7 is V plus, and 8 is not connected. That means if you want to make any connection for IC741, we can have two inputs, either 2 or 3, like inverting and non-inverting, and we can take output from pin number 6, and we need to provide the supply voltages plus VCC and minus VE at pin number 7 and 4 respectively. So we all are familiar with this, but if I will talk about the internal structure, then many of us may not be familiar with that internal structure. So today we will see the internal structure of IC741, and in this lecture we will discuss the bias circuit of IC741. That means today we are going to perform DC analysis of IC741. So just we can say that this is the internal circuit of IC741, which consists of these stages. Like this first stage is the reference current generation stage. Second stage is called, this is actually simple reference current generation stage. After this actual work start, and this stage is called as first stage. And in reference current generation, you can see there are two transistors. One is Q12, another one is Q11. And in first stage, this is reference current generation. In first stage, there is transistor Q9, Q8, Q1, Q2, Q3, Q4, Q5, Q6, and Q7, as well as Q10. After this, this is the second stage, which consists of the transistor Q13A and Q13B, Q16, Q17, and this is the coupling capacitor, which is used for the frequency compensation. And this is the output stage, which consists of transistor 18, 19, 14, and 20, 23. And the shaded portion shows the short circuit current protection circuitry, which consists of these transistors like Q15, Q21, Q24 and Q22. So now we will see that how does each and every transistor will get the DC current and DC voltage for the proper operation. So let us discuss. Before starting the discussion of the DC analysis, we should always remember the device parameters. Like for NPN transistor and PNP, IS is 10 to the power minus 4, beta is 200, VA, that is early voltage, is 125, and IS is 10 to the power minus 14, and beta is equal to 50, VA is equal to 50 for PNP transistor. And there are two transistors which we need to consider, like Q13 and Q13B. These are the device parameters. And there are two more transistors like Q14 and Q20. We need to consider it. That means when we will discuss them, they will have different value of IS. Okay. So now let us start the discussion. Let us see how much current will this reference current generation circuit will generate. See, this is forming a circuit in which if you will start from this plus VCC and this voltage drop will be VBE, and then voltage drop across this resistor, and then this voltage drop, and then you will reach to the ground. So you can simply write that I reference will be equal to this plus VCC minus this voltage drop VBE 12, which is this, minus VBE 11, which is this, minus VEE, which is this, divided by R5. So in this way you can find out the value of I reference. Actually, you know all values like VCC and VBE is plus 15, base emitter voltage is nearly equal to 0.7 volt. So we will have 0.73 milliampere, and this will be the value of I reference, and we need to remember this value. Now after this, if I will move to, this is what we have to remember from the reference current generation method. That means we need to remember the value of reference current. Actually, we will use this value. Now after this, if you will see here, this is the transistor Q10 and this is transistor Q11. They are forming current mirror circuit, and its name is actual name is Widlar's current mirror circuit. And for Widlar current mirror circuit, we know that I naught RE is equal to VT ln I reference upon I naught. So for this circuit, we can write VT ln I reference upon IC10 is equal to IC10 into 11. So this is what which we can write very easily for this. And in this case, you know the value of VT, you know the value of R4, you know value of I reference. So by Hutton trial method, you can find out that IC10 is 19 milliampere. Now let us move towards Q8 and Q9. This is again forming the current mirror circuit. Actually, in this analysis, what we are going to find out the DC current through each and every transistor. Now, let us consider that the current which is flowing in this terminal is 2I, or you can consider that this current is I, then this current will also be equal to I. These two are symmetrical and similar transistors and same branches. So I plus I, this current will be 2I. And by current mirror circuit for BJT simple current mirror circuit, I naught is equal to I upon 1 plus 2 upon beta. So this current is 2I upon 1 plus 2 upon beta. So you will get it. And this current is I, this current is also equal to I. Then this current will be equal to I divided by beta. This current will also be equal to I divided by beta. Then this current will be equal to I upon beta plus I upon beta, that means 2I upon beta. Beta P means for PNP transistor. So if you will see here, then this current plus this current will be equal to IC10. So we can simply write that 2I upon beta P plus 2I upon 1 plus 2 upon beta P is equal to IC10. So this is what which I have already discussed with you. This all has been written over here. So if you will consider, in this case, beta is much greater than 0, that means very large, then this factor will become almost 0. This factor will be 0, that means it will be 2I, and it will be nearly equal to IC10. You have already found out IC10, so you can find out I, and I will be equal to IC10 divided by 2. This is what which we have find out here. So we have already find out IC10, so I will be equal to half of 19 microampere, that means it will be 9.5 microampere. So after this, you can go back and you can see current flowing through transistor 1 is considered as IC1, IC2, IC3, IC4 like that. So we can simply write that IC1 is equal to IC2 is equal to IC3 is equal to IC4, which will be equal to 9.5 5 microampere. And now if you will move further downward to the first stage, then we will get it that this is Q7, Q5, Q6, and this is second stage that is going for the Q16. So if I will consider here that IC3 is I and base current is almost negligible, so this current will also be equal to I, and this current will be equal to I upon beta n, because IC is equal to beta IB and IB is equal to IC upon beta. So you know I is the collector current, then base current will be equal to I upon beta. Similarly, this current will also be equal to I upon beta. This current will be equal to I. This current will also be equal to I. So in this way, we can find out IC5 and IC6. If I will talk about IC7, see, this is IC7. That means this current will also be almost equal to this current. And this current will be equal to what? This is something which we need to take care, because we can, this somewhat different concept will be applicable over here. See, this current will be equal to this, apply KCL at this node, this current will be equal to summation of this plus this current. So these two current are equal to I upon beta plus I upon beta, that means 2I upon beta plus this current. This current will be equal to the voltage across this resistor, and voltage across this resistor will be the voltage across these two branches. That means VBE 6 plus this voltage. So we can simply write, actually this voltage is nothing but I and this resistor R2. So this is how we can write IC7 is nearly equal to IE7, which is equal to 2I upon beta. I upon beta plus I upon beta is 2I upon beta plus this VB is 6 plus IR2. This is the voltage, and current will be equal to divided by R3. So this is how we got this value. So you know, for transistors, we know this, that base emitter voltage is equal to VT ln I divided by IS. So if you will, you know all the values, you know IS, you know, you have already found out I. So you can find out that VBE6 is equal to 517 millivolt. So if you will put in previous equation, you can get IC7 in this equation. Now you know value of I, you know value of beta, you know value of VB6, you know these two values, you know value of R3. So you can find out that IC7 is 10.5 microampere. So for any case, that means if you want to find out the bias current, you know bias current is the average of 2 and offset current is the difference of 2 and their mode. So I think it should also be clear that now we know that what or how much current will flow through the transistor of first stages and reference current generation stage. So now let us come back to the second stage, and you know that this is the second stage, which consists of Q16 and Q17. So in Q16 and Q17, if you will neglect the base current of Q23, then collector current of Q17 will be approximately equal to the current applied by the current source, that means Q13B, and we know Q13B has a scale current of 0.75 times of Q12. So we can simply write, you have already found out the value of the current which is flowing through Q12. So you can find out that IC13B is 0.75 times of I reference, and we are assuming that beta P is much greater than 1. So IC13B will be 550 microampere and IC17 will also be equal to 550 microampere. So, VB is 17, which we already know that base emitter voltage is equal to VT ln IC upon IS, that is the reverse saturation current. So, we know these all values. So, we can find out VB is 17 is equal to 618 milliampere. So, just to find out IC 16 and IC 17, we can apply Kirchhoff's current law just as in case of first stage. So, you will get IC 16 is equal to 16.2 microampere. So, this is how we can do the DC analysis of first and second stage. Now, let us move towards the output stage. This is the transistor Q13A, and in this case the reference current will be the 0.25 times of I reference, and this is Q18, Q19, Q14, Q20, Q23, and I have already eliminated the short circuit current production circuitry. Don't get confused, because in the internal structure of IC 741 you can have few more transistors which are connected over here and 2 resistors, but here I am not considering this short circuit current production circuitry. I am simply considering the output stage, the components, the transistors, the resistors which are responsible for the output stage. I am going to taking care of those elements only, and let us come to the discussion. And you know, IC 23 and IC 23, this whole current will go over here. If I will consider that this current is negligible, then I can write that IC 23, which is nearly equal to IE 23, it will be equal to 0.25 times of I reference. And you know, I reference, if you will multiply it, you will get it is equal to 180 microampere. So, we can see that the base current of Q23 is, you can divide it by 50. That means 50 is the value of beta. So, you will get 3.6 microampere, and we know that this is quite negligible in comparison to the IC 17. Actually, when we were analyzing the second stage, that time we considered that IC 17, base current of this Q23 is very small or negligible, so which is proved over here. Now, the emitter current of Q18 will be this 180 minus 15, this 180 minus 15. So, you will get it is equal to 165 microampere, and IC18 and IE18 which are equal, so nearly equal, so you will get it is equal to 165 microampere. So, you know, we can find out that VB18 is 588 millivolt, which is quite close to the value which we used to assume. So, the base current of Q18 will be 165 upon 200, because 200 is the value of beta for Q18. So, this current will be added to the current in R10, and we can find out the value of IC19 and IE19, which are nearly equal. So, you will get that it is equal to 15.8 microampere. This 15 plus this 0.8. So, you will get 15.8 microampere. Okay. Don't get confused. This 15 ampere we are getting from the current through R10. This, what will be this current? This voltage which is coming in parallel with this divided by this resistor will be this value. So, this is how we can find out the IC19. That means we have the value of all the currents which are flowing through various transistors. Now the voltage drop across the base emitter junction of Q19. This is the generalized formula for base emitter voltage. So VB19 is equal to VT ln IC19 upon IS. It will be equal to 530 millivolt. Similarly, we can find out for Q18 also. That means VB18. So if you will add VB18 and VB19, which is we are calling as VB, it will be equal to 588 plus 530, and it will be equal to 1.18 millivolt. So now if you can put these values of this transistor Q14 and Q20, see 18, 19, this voltage drop will be equal to the voltage drop over base emitter junction of Q14 and Q20. That's why we are putting these two equal. This VBB and this is the base emitter voltage which is going to appear across Q14 and Q20. So now you can put the value of IS14 and IS20, and from the diagram you know that collector current of Q14 and collector current of Q20 is equal. So you can easily find out that IC14 and IC20 is equal to 154 microampere. So here we can conclude that we have found out the current through each and every transistor. This is what we have to do in the DC analysis of the IC741, or this is which we have to do in the bias circuit analysis of IC741. In next lecture, we will discuss the small signal analysis of IC741. Thank you.